Hello, Miss Teasley here. We're going to wrap up our unit on functions and limits. If you do hear any background noise, that's my fan blowing in my face. So sorry about the background noise if you hear that. But let's go ahead and get to it. This is continuity. All right. So in algebra, when I ask you if a graph is continuous or discontinuous, you will look at it as whether you can draw the graph without lifting up your pencil. So for example, these three graphs here are discontinuous graphs. All right. The first one, if I start drawing this graph, when I get to that hole, I have to lift up my pencil, draw the circle, and continue on. So that's a discontinuous graph. Second one here, you have a vertical asymptote. I have to draw this piece of the graph, lift up my pencil, and then continue on with this second piece of the graph. So again, it's discontinuous at the vertical asymptote. And then the last graph is discontinuous. I get here, I have to lift my pencil, draw the circle, jump down here, continue on, and sketch this piece of the graph. So all three graphs listed here are discontinuous graphs. There are two types of discontinuities, and they are removable and then non-removable. The only removable one is the hole in a graph, and that's because you can easily make that graph continuous by replacing the hole with a point. The other two are non-removable. So the non-removable discontinuities are vertical asymptotes, and the other one will be a jump. So when we get down to this first example, they want us to list the intervals on where the graph is continuous and list the points at which the graph is discontinuous over the interval from 0 to 5. So let's start off with the points of discontinuity. All right, so it's discontinuous discontinuous at x equals 1, 2, and 4. All right, let's go down the list. And if you notice, at 1, I have that open circle, that's a hole. So x equals 1, there's a hole. At x equals 2, there's a vertical asymptote. So vertical asymptote. And at x equals 4, there's a jump in the graph. All right, so x equals 4, there's a jump. The first one, the hole, is removable. All right, so I'm just going to put R for removable. And then x equals 2 and x equals 4 are non-removable. So non-remove, I'll just say. All right, so those are the 3 points of discontinuity. They tried to trick us with this 3. They put a dark circle there at 3, but that I can put dark circles everywhere on this graph. So at 3, it's still continuous. So the only 3 places where it's discontinuous is at x equals 1, x equals 2, and x equals 4. The intervals where it's continuous, all right, you always read your graph from left to right. It's continuous on the intervals from 0, starting with, and you use x values. So from 0 to 1, all right. So you include the 1, even though 1 is not included, put a parentheses. So it's continuous from 0 to 1. And then, so if I trace from 0 to 1, and then from 1 to 2, so 1 to 2. And then I will have to continue on from 2, all right, and we know 2 is not included, that's why we put parentheses, from 2 all the way to 4, union. And the last part is from 4 to 5. Notice where it breaks apart. 1, that's where it's discontinuous, that's the hole. Then you have the 2, from 2 to 2. So notice how 2 shows up in both places. That's where it's discontinuous, that's your vertical asymptote. And then it's also discontinuous at 4. 4 is here and 4 is there. All right, so that's the intervals where it's continuous. It breaks apart at the discontinuous points. So again, in algebra, easily to recognize that something is continuous. If you have to lift up your pencil at a certain point, that's what a graph is discontinuous. In calculus, they have a more fancier definition of continuity. All right, so being continuous, and it's continuity at a point. It said a function y equals f of x is continuous at point C if the limit as x approaches C is the same thing as f of C. So that means that the limit will have to exist. It has to be the same on both sides, and it has to be equivalent or equal to the function value at that particular x value. All right. So moving on to example 2, the direction reads, for C equals 1, 2, and 4, find f of C. The limit as C approaches, the limit as x approaches C from the right, the limit as x approaches C from the left, and the limit as x approaches C. Take notice how each part of the definition of continuity is important. So clearly, if you look at this graph, it's not continuous at 1, it's not continuous at 2, and it's not continuous at 4. We talked about that in the last example, all right? But they want you to see how the limit ties into this. So starting with the first one, at x equals 1, the limit as x approaches 1 from the right of f of x. So from the right of f of x, the limit as x approaches 1, as I get closer and closer to 1 from the right, it goes to 1. The limit as x approaches 1 from the left of f of x. So coming to this vertical line, the limit as x approaches 1 from the left is also 1. The limit, so therefore the limit as x approaches 1 of f of x just equals 1. But f of 1 equals 3. So because these 4 values are not all the same, that means that the graph is not continuous at 1. All right. So because even though the limit is 1, because the left and the right side of limits are the same, the function value is 3. So if you saw that information, if you didn't have a graph in front of you, you should already know that this graph is not continuous at x equals 1, because all those values are not the same. The same thing for x equals 2. Let's look at the left right-handed limit, and then let's look at the function value. So the limit as x approaches 2, let's do the left side first, from the left of f of x. So as x approaches 2 from the left, all right, so let me use a different color. So this is the piece of the graph that's approaching 2 from the left. It's going all the way up here to infinity. The limit as x approaches 2 from the right of f of x. In this case, so from the right, it's also going to infinity. But remember what I told you, limits don't exist at vertical asymptotes. So the limit as x approaches 2 of f of x is a d and e, and that's because infinity can't equal infinity. All right. F of 2 is a d and e. So again, by definition of continuity, this graph is not continuous at x equals 2 because all 4 values are not the same. All right, so all 4 of these values will have to be the same for something to be continuous. And again, yes, we see the graph. You can clearly see there that the first one had a hole, the second one has a vertical asymptote. But what if you didn't have a graph? All right, you would need to be able to take this information and be able to gather that it's not continuous at these particular points based on the information. All right, and the last one at x equals 4, the limit as x approaches 4 from the left of f of x. So let's see, let me use a different color. So as I approach x equals 4 from the left, this limit is 2. The limit as x approaches 4 from the right of f of x. So coming from the right this time, and notice how I put those vertical lines. That's helpful when you know your limits. As I approach it from the left, the limit is 1. Therefore, the limit as x approaches 4 of f of x is d and e, And that's because these two numbers are not the same. F of 4 is the dark circle, which is 1. So, again, this graph is not continuous at x equals 4 because all 4 of these values will have to be the same in order for it to be continuous. And so notice what it says, you don't always get a picture, so you will have to be able to do this algebraically as well. All right. So, moving on. Determine whether each function is continuous or not. If it is not continuous, use the definition of continuity to explain why. Well, you can look at the graph of these. So let me open up Desmos. All right, the first one. The first one was 1 over x minus 1. So 1 divided by x minus 1. So here's a graph. You should be able to see that x is not defined at x equals 1. All right, and there is a vertical asymptote at x equals 1. So let me just go ahead and actually graph that. X equals 1. There's your vertical asymptote, x equals 1. So this graph is not continuous at x equals 1. So I will write down my different limits. So at x equals 1, there's a vertical asymptote. All right, that's considered a non-removable discontinuity. Let's look at the different limits. All right, the limits as x approaches 1 from the left of f of x. If I go to my graph, the limit as x approaches 1 from the left, it goes down to negative infinity. And from the right, it goes to positive infinity. So this is negative infinity. The limit as x approaches 1 from the right of f of x is positive infinity. Therefore, and even if these were the same infinities, the limit will not exist because there's a vertical asymptote. So the limit as x approaches 1 of f of x is a d and e. And then f of 1 is a d. So again, because these 4 values are not all the same, it's not continuous at x equals 1. All right, there's a hole. Part B. All right, I'm going to, I see that x is not continuous. Well, there is something going on at x equals negative 2 because negative 2 plus 2 gives me 0. So I know x can't equal negative 2. We could look at the graph at this. Let me do it algebraically. Let's just simplify it and see if we can factor this out at the top. So if I do 2 sliding divide 2 times this 6, I get 2x squared plus, I moved the 2 out the way. So slide the 2 down and I get x squared plus x minus 12. When you factor that, 2 numbers that multiply and give you a negative 12, but have to add and give you a positive 1. So that would be x plus 4 and x minus 3. Then you come back and divide both numbers by 2. Move this out of the way. So now when I do that, I get x plus 2. This 2 goes in front of that x, so that's 2x minus 3. So factor form is 2x minus 3 times x plus 2 all over x plus 2. Because the x plus 2 cancels out, that means there is a hole at x equals negative 2. All right, so x equals negative 2, there's going to be a hole in the graph. So let's get a visual. Let me pull up Desmos and let's look at the graph of this. So 2x squared plus x minus 6. So divide 2x squared plus x minus 6, and it was over x plus 2. So I told you something is going on at x equals negative 2. So x equals negative 2. Let me see if I can get it to show where it's undefined. There it is, negative 2. All right, so you have to actually, negative 2 is undefined. So that means there's a circle there. There's a hole in the graph. So we know there's a hole in the graph. The limit. All right, let's look at the graph again, the limit. The limit as, let's put in x equals -2 so we can get a visual. So if I need to find a limit on the left and the right side, it looks like the limit as x approaches -2 on the left and the right side are both going to be -7. That's where they meet, at -7 on both sides. All right, so let me put that down. So the limit as x approaches -2 from the left of f of x is -7. The limit as x approaches -2 from the right of f of x is also -7. So therefore, the limit as x approaches 2 of f of x is -7. But f of, this is -2, f of -2 is a D and E. And we saw it with the graph, you saw it visually, is it does not exist. If you plug -2 into this equation, it's going to be undefined. And again, because all four of these numbers, the -7s and the D and E, they're not all the same, the graph is not continuous at x equals -2. To find the limit algebraically without looking at the graph, you would take this 2x minus 3 and plug in -2. So if I need to find the limit as x approaches -2, after I simplify, I will plug it into this 2x minus 3. So this is 2 times -2 minus 3. So this is -4 minus 3, which is -7. All right, so this is the algebraic way of getting the answers that I have up here at the top. All right, that's ugly, but it's okay. All right, so it's not continuous. Here at part C, to figure out if this graph is continuous or not, I want to plug in 1 into both equations. All right, because that's the only possible place looking at these functions where it could be discontinuous. I don't see any rational functions. I don't see any fractions. So there's nowhere where it's undefined on this line or on this quadratic. I just need to make sure that the same values are the same for x equals 1. So I'm going to plug x equals 1 into -2x plus 3. So let's see what I get. -2 times 1 plus 3 is -2 plus 3, which is 1. Then I'm going to plug in 1 into the x squared equation. Well, 1 squared is 1. Well, since these two numbers are the same, that means that this piecewise function is continuous. All right, it's going to be continuous. There's no holes or gaps here. We also can look at in terms of the limit. If I ask you to find the limit as x approaches 1 from the left side, all right, of f of x, it would be the same thing. I would plug 1 into this first equation, and we already know the answer is 1. If I needed to find the limit as x approaches 1 from the right side of f of x, I would take the 1 and plug it into the second equation. So I will take 1 and plug it into the second equation, and I will also get 1. So therefore, the limit as x approaches 1 of f of x is 1. And f of 1, I will use this equation, f of 1. That's where x equals 1. I plug in 1, 1 squared is 1. All right, so since all four of these numbers are the same, the limits and the function value are the same, it's continuous. This is a shortcut way over here. If you just take wherever, like if you needed to know if the graph is continuous, if you look at where it splits off, plug that number to both equations and see if you get the same y value. Because if you do, then it's continuous. All right, let me show you a visual of this because you do need to know how to graph these. I want to show you how to graph it in Desmos. So -2x plus 3 and x squared. So I will type -2x plus 3. And then you put your restrictions and braces. So this is where x is less than 1. Was it 1 or -1? Let's see. X is less than 1. So that's that first part. And the other one, which is x squared, put your restrictions and braces, and this is where x is greater than or equal to 1. So notice how the graph connects. All right, and it connects when x equals 1, it connects at the y value of 1. All right, they both have a y value of 1. All right. All right, so the last part, use the definition of continuity to find the value of a so that g of x will be continuous for all real numbers. So when we use that little shortcut that I showed you, what you want to do is you want to plug in 1 into both equations. And you set them equal to each other, because if they're continuous, the y value should be the same. So let's start off by just setting the equations equal to each other. X squared plus 7 equals x plus a. And then you're going to plug in 1 for a. So we're going to replace x with 1. So let's make a note, replace x with 1. So when I do that, I get 1 squared plus 7 equals 1 plus a. So this is 1 plus 7 equals 1 plus a. So this is a equals 1 plus a. To solve this equation for a, subtract 1 from both sides. So I get a equals 7. So I'm saying that in order for this graph to be continuous, a will have to be 7. So that turns this equation into x plus 7. So let's look at this on Desmos so you can get a visual. So x squared plus 7 and x plus 7. So I have x squared plus 7. The restrictions on that part, the restriction is x is greater than or equal to 1. So, all right, x is greater than or equal to 1 on the first one. So restrictions, x is greater than or equal to 1. And then the other graph, you have x plus 7. And I'm assuming this is x is less than 1. All right, so there's your graph. It's continuous at x equals 1. And that actual value where it's continuous, it looks like it's continuous at 6, 7, 8. All right, and when y equals 8. All right. Yep, because if you plug 1 into both of these equations, you'll get an 8. So if I just double check it, 1 squared plus 7 equals 8. 1, if I plug it into this equation, 1 plus 7 also equals 8. So it's continuous. All right, use the definition of continuity to find the value of a so g of x will be continuous for all real numbers. So when you see problems like this where x equals the number or can't equal the number, to find the limit, you plug the limit into this equation. All right, that's how you calculate the limit. And then the function value is going to be the whole part. So in order for it to be continuous, all these values have to be the same. So the limit as x approaches 1, I'm going to plug it into this x minus 4 minus 1 all over x minus 1. If I plug 1 into this, it's undefined, but you need to factor. So that's the next thing. You want to factor this. So I get x squared minus 1 times x squared plus 1 over x minus 1. Move this out of the way. All right, now I can factor this some more. This x squared minus 1 can be factored more. So that's x minus 1 times x plus 1. That's how that factors. That x squared plus 2 cannot be factored, so I leave it as x squared plus 1 cannot be factored, so I leave it as is, x squared plus 1 over x minus 1. Cancel out the x minus 1. All right, that's what the goal is, to get rid of that x minus 1. So now I can plug 1 into this equation. All right, so to finish this off, I'm going to plug 1 into here. So this is 1 plus 1. I don't need these fancy. All right, let me write down what I have. So this is the limit as x approaches 1 of x plus 1 times x squared plus 1. To find the limit, you plug in 1 plus 1, 1 squared plus 1, which looks like this is 2 times 2, which equals 4. All right. So the limit as x approaches 1 is 4. All right. So therefore, at x equals 1, this will have to be a 4. All right. So a has to be 4. All right. Let me show you what this looks like as a visual. All right. So a will have to equal 4. So let's put this in as a piecewise function. Let me see if you can do that in Desmos that x cannot equal to. Let's see. So I have x to the 4th minus, x to the fourth minus 1 over x minus 1. All right, make sure I typed it in correctly. All right, and it says that x cannot equal 1. I don't know. Let me try this symbol. This will be my first time trying this. Let me see if they even have that symbol. I don't see a cannot equal to symbol. All right, let me see if they have it here. Nope, there's no cannot equal to. All right, so basically, let's see what's going on at x equals 1. So at x equals 1, all right, if you notice, if x equals 1 up here, I'm hitting where they intersect. Sometimes you can. All right, if you notice, they intersect at that point 4. All right, if you look at the y value where they intersect, it will be 4. So at x equals 1, that y value will have to be 4. So in that case, a equals 4. All right, so find your limit. In order for this graph to be continuous, there will have to be a point at x equals 4, because right now x equals 1 is undefined. There's a hole there, but in order for me to fill that hole, remember it's called removable, you will have to have a y value of 4 at x equals 1. All right, that looks like that's all. So your assignment is attached to this. Check Canvas or the board for the homework assignment, and that's it.